Hello, welcome to the AA Solutions channel. In today's video, we're going to be walking through an example on the application of Lagrange equation to deriving equations of motion for a vibrating system. And we're going to quickly commence by just trying to describe the Lagrange equation in itself. Then we'll proceed to look into how to apply it to evaluating equations of motion for a particular system that will be given. This is the Lagrange equation, but there are descriptions to each and every of the terms that are contained in the Lagrange equation. We have L, which is the Lagrange formulation, and it's just equal to T minus V, where V is the potential energy, that's the total potential energy of the system. T is the total kinetic energy of the system as it is vibrating. Then we have Qi. Qi is the generalized displacement of the system. Then we have Qi dots. That's the generalized velocity. Once you have generalized coordinates and you find the derivative with respect to time, what you have is generalized velocity. Then there is capital Qi. That's the generalized force acting on the system, which is a function of the virtual work in the system as a result of damping. So W is the work done in dissipating energy from the system when there is damping or there is any form of friction in the system. And W has a simple formulation wherein is equal to the integral of the product of the damping coefficient and the generalized velocity with respect to displacement. And we have another form of the Lagrange formulation as shown. However, when you choose to use will give you the same equations, of motion at the end of the day. So we're going to move forward to evaluating our problem. If we have this system, which is a collection of pulley systems and masses that are connected to each other, and we want to see how the vibration will progress for this particular system. If we take the first part of the pulley and we assume it to be undergoing torsional vibration, that is, it's rotating to and fro about its axis. If in an instance we give this pulley a clockwise rotation, the spring K1 will likely compress, and as a result of that, every other part of the system may not be affected by that rotation that is given to pulley I1. So we can say that pulley I1 can have independent torsional vibration that does not affect all other parts of the system, and we can call that the first degree of freedom of the system, and we can describe that with theta 1. So at every point in time we can describe just the position of the pulley by theta 1. Then if we look at the second part of the system and we decide to give pulley I2 a form of displacement either in the clockwise direction or the anti-clockwise direction, we would observe that the mass M2 will be displaced correspondingly with the movement of pulley I2. Spring K2 may be compressed as well, and when spring K2 is compressed, it may not affect the movement of mass M1. As a result of that, mass M1 may not be affected by the movement of pulley I2 as well as pulley I1. So we can call that the second degree of freedom, and we can call that theta 2. Then finally, a third part of the system, which is the movement of mass M1. If M1 is displaced, say it's given upward or downward displacement, we discover that spring K2 will be either compressed or extended as a result of the displacement of mass M1, and this may make the movement of mass M1 not affect all other parts of the system, and as a result we can say mass M1 could be vibrating on its own independently without affecting other parts of the system, and we can give the generalized coordinate for the movement of mass M1 to be x. So we're going to try to solve this problem quickly, and we've identified our generalized coordinates to be theta 1, theta 2, and x. So one can quickly say that I is equal to, when I equal to 1, we have Q1 to be theta 1. And when I is equal to 2, we have Q2 to be theta 2. And when I is equal to 3, we have Q3, we have Q3 to be equal to X. The next thing we want to do is to call out our Lagrange formulation. And our Lagrange formulation says d dt, dl dqi minus dl dq, dl dqi dot minus dl dqi is equal to our generalized force. So, and we know that L is equal to T minus V. And what is T? T is the total kinetic energy acting on the system. So we're going to write out the total kinetic energy due to pulley I1, pulley I2, mass M2, and mass M1. So the total kinetic energy of pulley I1 is equal to half multiplied by I1, and is going to be theta 1 dot square. We know that velocity is half mv square, where v is velocity. So we're going to take the kinetic energy of the second pulley, which is going to be half times I2 theta 2 dot square. Then we'll take the velocity, the kinetic energy of mass M2, half M2. For this case, what is the velocity of mass M2? It's going to be a function of the movement of, as a function of velocity of theta 2. If this pulley is rotated, say in the anti-clockwise direction, this mass will likely move upwards by the total distance that the pulley has been rotated. And we know that linear distance, let's say it's xx, is equal to radius times angular distance. And knowing this, for this case, because it's velocity, so if we have x dot dot, it will be equal to r times theta dot. So because we are taking that velocity, we're going to have this mass M2 as r theta dot. For this case is theta 2, and this is going to be squared. And finally, the last mass, M1. M1, the kinetic energy for M1 is going to be half M1 times the distance moved, the velocity times the velocity of M1 squared. And this case, M1 at every point in time will be vibrating with a velocity x dot. The next thing we want to evaluate is the potential energy acting on the system. Potential energy V is equal to the potential energy of all the springs in the system. For this case, there are no potential energy due to gravity because the systems are all connected to themselves. Potential energy for spring 1 is going to be half times the spring 1 constant times the displacement of the spring at every point in time. Let me quickly illustrate what the displacement of this spring would be per time. Displacement of this spring would be the difference between the displacement of the spring as a result of this pulley I1 and pulley I2. So we're going to have displacement of the spring to be, let's say, pulley I1 minus displacement due to pulley I2. And displacement due to pulley I1 is the linear displacement as a result of the rotation of spring pulley I1. And linear displacement is simply the product of radius times angular displacement. And if you do same for the second spring, you have also radius multiplied by the displacement R2. So this becomes the linear displacement of the spring. And spring, potential energy due to spring is equivalent to half times K1 in this case multiply by the displacement squared. Then if we look at spring K2, the potential energy in spring K2 is half K2 multiplied by the displacement at every point in time of spring K2. In this case, spring K2 will be affected by the displacement X and also the displacement as a result of pulley I2. And the displacement as a result of pulley I2 is the product of the radius times the angular displacement of pulley I2. For this case, we are using small radius r because the string is attached to the smaller pulley that has radius r. So therefore, the potential energy as a result of spring K2 is equivalent to half K2 multiplied by x minus r theta 2, and we have all squared. And finally, the third spring K3 at every point in time will be displaced by the distance that pulley I2 is making it to move by. And this case, we're going to have just r, which is the bigger radius, since this string is attached to the bigger pulley, multiplied by our theta 2, which is the angular displacement pulley I2 would have moved. So for the third part, or the potential energy due to spring K3 will be half K3 multiplied by r theta 2 all squared. So having gotten the potential energy, we want to quickly find our Lagrange function, which is L is equal to T minus V. So we're going to subtract T from V. And if we subtract that, we are going to get half into I1 theta 1 dot square plus half I2 theta 2 dot square plus half m r square theta 2 dot square plus half m1 x dot square. Sorry, this is m2 minus, we want to start subtracting the terms of the potential energy now. So we have minus the first term of the potential energy, which is half K1 r theta 1 minus r theta 2. So here we have minus half K1 into brackets r theta 1 minus r theta 2 squared minus the second term, which is half K2 into brackets x minus r theta 2 all squared, and minus the third term, which is equal to half K3 r squared theta 2 square. And this is our Lagrange formulation. So having gotten the Lagrange formulation, we want to begin to derive the different equations of motion of the system. So we're going to start with when I is equal to 1. And when I is equal to 1, we have that Q1 is equal to theta 1. And Q1 dot is equal to theta 1 dot. And our Lagrange formulation becomes, so to write out our Lagrange formulation as it applies to this first equation of motion, we have that d dt into the L, the theta 1 dot minus the L, the theta 1 is equal to 0, knowing that our generalized force is 0 since the system has no damping. So we want to begin to look for all the terms one per time. We're going to start with this term. To look for that term, we have the L, the theta 1 dot, which means we want to differentiate the whole of these L terms. We want to differentiate the whole of these L terms with respect to theta 1 dot. That's with respect to the velocity in the first coordinates. And to do that, we look through all the terms. If we look at the Lagrange formulation closely, you discover that this term has theta 1 dot. There is no other term having theta 1 dot. If you look closely, this is the second term has theta 2 dots, the third term has theta 2 dots, the fourth term has x dots. The fifth term has just theta 1 and theta 2, no theta 1 dots, no theta 2 dots. And by the time we differentiate with respect to theta 2 dots, theta 1 with respect to theta 1 dots, we are likely going to have 2 times half I1 theta 1 dots, and 2 we cancel that 2, and that will then will be left with I1 theta 1 dots. To look for the term D, the L, the theta 1 dots, which constitutes the first term that we are still battling with, we are going to get d dt I1 theta 1 dots. And knowing that the second moment of inertia of the pulley I1 is constant, if we differentiate velocity with respect to time, we get acceleration. So that can easily be written as I1 theta 1 dot dot. The next thing is to look for the second term, the L, the theta 1. And to do that, we are going to differentiate all of our L term. Let's recall that we've estimated L earlier here. And what are the terms that has theta 1 in it? The first term has theta 1 dot, no theta 1. The second term has theta 2 dot, no theta 1. The third term has theta 2 dot, no theta 1. The fourth term has x dot, no theta 1. The fifth term has theta 1. So we're going to differentiate that term. The sixth term has no theta 1, and the seventh term also has no theta 1. So every other term will vanish from the equation when we are differentiating, and we're going to have just this term. So our dl, the theta 1, is going to be 0 for all the terms, minus, of course, if we differentiate this term that we are working with, we are going to have 2 multiply by half times k1, or multiply what we had inside before, r theta 1 minus r theta 2. The square will disappear because we are differentiating, so the square has come inside. And also we are to multiply by what we get when we differentiate what we have inside the brackets, and that will give us r, so we are to multiply by r. In case you don't understand that this was differentiated, that's how we differentiated half k1 into bracket r theta 1 minus r theta 2 bracket close square. You just go and look at how you differentiate function of a function, and easily you will get this equation. And that will be, if you simplify further, knowing that 2 we cancel out 2, what will be left with will be half will be k1 r square into theta 1 minus theta 2. And as a result of that, considering that we've written out our Lagrange equation earlier, so we're going to, based on what we've written out, write out our equation of motion. Going back to our Lagrange equation, having determined the different terms that we want to work with, you can easily write out our equation The first term, we calculated the first term to be I1 theta 1 dot dot. So if we write that out, we have I1 theta 1 dot dot minus our second term, which is minus k1 r square theta 1 minus theta 2. And if we do that, minus k1 minus, we multiply minus to turn this to plus, so we have k1 r square theta 1 minus theta 2. All of these will be equal to 0, and this is our first equation of motion for the vibrating system. So we are going to continue to determine our second equation of motion for this system, and for that case we have that I is equal to 2, so our Q2 is equal to theta 2, and our Q2 dot is equal to theta 2 dot. And we've derived our Lagrange formulation before, so we're not going to work that out, we're just going to write it down. So this is our Lagrange formulation that we derived earlier. So we're going to progress from here, and to do that we want to recall our Lagrange formulation. For this case, for the second equation of motion, so we're going to have d dt, and we have the derivative of the Lagrange formulation with respect to velocity term. So we have theta 2, which is for the second one, theta 2 dot, which is for the second equation of motion that we intend to derive, minus the L with respect to the minus the L d theta 2. We say this is equal to 0 because all qi terms are 0. So the next thing we want to bother ourselves with is to begin to find each and every of all the terms. To find the first term, which is this, beginning with this side of the equation, we are going to get the L d theta 2 dot. To find the L d theta 2 dot, we have to look through the L, and all the terms that has theta 2 dots, we differentiate them and write out our answer here. So if we look through the equation, the first term, which is half I1 theta 1 dot square, has no theta 2. The second term, of course, has theta 2 in it. So we're going to start by differentiating this term. And if we differentiate this term with respect to theta 2, we are likely going to get 2 times half, which will disappear the half. So what will be left is I2 times theta 2 dot. Then the next term also has theta 2 dot. The next term, which is half m2 r square multiplied by theta 2 dot square. If we differentiate the whole of this term, we are going to get, of course, we bring in our sign plus half, we multiply 2, and that will disappear the half. So we're going to, what will be left is m2 r square theta 2 dot. And if you look through the equation, there's nothing else having theta 2 dots. The only time we saw theta 2 again, it does not contain dots. It's just r theta 2 and small radius multiplied by theta 2 in the fifth term. Having gotten this, the next thing we want to find the derivative with respect to time of the L the theta 2 dots, so that we know we're done with the first. This quickly, it's equal to, if you differentiate this with respect to time, I2 is constant, but theta 2 is velocity, is a function of time. So if you differentiate with respect to time, you get acceleration. So that becomes I2 theta 2 double dot, which represents acceleration. And if you do same for the other one, we have m2 r square is constant because radius is constant, mass is constant. But if you differentiate theta 2 again with respect to time, you get acceleration, which is theta 2 dot dot. So the next thing we want to do is to find the derivative of the second term which is dl d theta 2 of our Lagrange formulation. To do that, we have dl d theta 2, which means differentiate all terms containing theta 2 in the Lagrange formulation to be able to get a value here. So if you differentiate this term, dl d theta 2, starting with the first term that we have, minus half k1 r theta 1 minus r theta 2 all squared, we are going to have minus, our minus remains, the 2, which is the power, is going to multiply half, so we still have our k1 there, and you have r theta 1 minus r theta 2. The square is left because we are differentiating the power first. Then we need to multiply by the term you get when you differentiate the core. That's what is inside with respect to theta 2. If you differentiate what we have inside with respect to theta 2, we are going to get minus r multiplying the whole of that. Then we're going to look through our equation to determine which other term has theta 2. It can be observed that the fifth term in our Lagrange formulation also has theta 2. So for differentiating this term also with respect to theta 2, we are going to get minus. Our minus sign remains as usual, so we're going to get minus. This also has power, so 2 times half times k2 into brackets r theta 2 minus x. Of course, the power is left, and if you differentiate the inside, what you likely get is r, so you multiply that by r. If you simplify this further, we will get dl d theta 2 is equal to k1 into bracket r theta 1 minus r theta 2, all multiplying r, minus 2 would have cancelled the half, so we have just k2 r theta 2 minus x into bracket r, and this is the second term. So if we bring out all these terms together, considering our Lagrange formulation here, bringing all terms together, the first term d dt dl d theta 2 dots, we got I2 theta 2 dot dots plus m2 r square theta 2 dot dots. Then we have minus the other terms, which is the l, the theta 2. So we have minus k1 into brackets r theta 1 minus r theta 2, or multiplying r, and the minus will multiply the minus for the other side, and this becomes plus k2 r theta 2 minus x multiply r, and this can be simplified further. You may want to work it out to get I2 theta 2 dot dot plus m2 r square theta 2 dot dot plus k1 r square theta 2 minus theta 1 plus k2 r theta 2 minus x times r, all will be equal to 0. And this constitutes our second equation of motion for the system. So we are going to quickly from there determine the equation of motion for the third degree of freedom. For this case, I is equal to 3. So we have q1 is equal to x, that's q3 is equal to x, q3 dot is equal to x dot. And if we write out our Lagrange formulation again, it becomes d dt dl dx dot minus dl dx is equal to 0. And we've derived our Lagrange equation earlier. A Lagrange formulation, we have it as d dt dl dx dot minus dl dx is equal to 0, having that there are no damping in the system. So if we work out the first term from here, we're going to get dl dx dot to be equal to, that means we want to differentiate the Lagrange formulation with respect to s dot. What are the terms having s dot? This one does not have s dot, this one doesn't have s dot, this one doesn't have s dot. Yes, this term has s dot. So we need to work out the derivative of this term with respect to x dot, noting that there's no other term having x dot in the equation, and that is going to be, when you differentiate that term with respect to s dot, you are likely going to get 2 times half m1 x dot. The square would have left, and of course if 2 cancels out 2, we are going to have m1 s dot. And mind you, the term we are looking for is d dt dl dx dot. So this will be equal to d dt of mx dot. If mass is constant and x dot is velocity, if you differentiate that with respect to time, you're going to have mass times acceleration, which is mass times x dot dot. And this is the first term. So to work out the second term, dl dx, we are going to have dl dx to be equal to the derivative of the Lagrange formulation, all the terms that has x. The first term in the Lagrange formulation does not contain x. The second term does not contain x. The second term has just theta 2 dots. The third term does not contain x. All it has is x dots. The fourth term does not contain x. All it has is theta 1 and theta 2. Then the fifth term, of course, contains x. The sixth term does not contain x at all. So to work out this, differentiating this term with respect to x, we are likely going to get minus half k2 multiplied by 2 into brackets r theta 1 minus x. The square would have disappeared because we are multiplying by 2. Then we are going to multiply by what we get when we differentiate the core. That's what is inside. And if you differentiate the core, this term disappears because there's no x there. What will be left is minus x, and when you differentiate minus x, you get minus 1. So this is minus 1 multiplying the whole of the equation. And at the end of the day, we'll be left with k2 into bracket r theta 1 minus x. So if we bring in all the terms back into our Lagrange equation, we have mx dot dot minus k2 r theta 1 minus x to be equal to 0. And this can be rearranged to be mx dot dot minus k2 into x minus, this becomes plus k2 into x minus r theta to be equal to 0. And this is the third equation of motion of the system. So we're quickly going to write out the three equations of motion of the system. And to write out our three equations of motion of the system, we have our first equation of motion to be I1 theta 1 dot dot plus k1 r square theta 1 minus theta 2 to be equal to 0, and our second equation of motion to be I2 plus m2 r square theta 2 dot dot plus k1 r theta 2 minus theta 1 plus k2 r theta minus x, r theta 2 minus x plus k3 r theta 2 is equal to 0, and finally m1x dot dot plus k2 x minus r theta 2 is equal to 0. These are our three equations of motion of the system. And the final equation so that will be all about our problem that we solved. I sincerely do hope the video was clear enough. I want to thank you for your time you spent to view this video, and I hope to see you more often.